We have three of them in this session. Professor Carlos Coello from the Departamento de Computación in Mexico. Our professor is an eminent distinguished scientist in the area of evolutionary multi-objective optimization. So he wants to speak with us from his wealth of experience in this field of computing. Over to you, Professor Carlos Coello, while we wait for the other professors in the session. Thank you.
Okay, thank you. I'm going to share my screen.
Yes, you can.
Let me see. Can you see my screen there?
Yes.
Okay. Then I'm ready to start. Well, first of all, thank you for the invitation. It's a pleasure for me to give this talk on an area in which I have been working for about 26 years. And it's called evolutionary multi-objective optimization. So I'm going to give you first a very short introduction to what EMO is. Basically, we have to understand first the difference between traditional global optimization and multi-objective optimization. In multi-objective optimization, the aim is to solve problems that have two or more objectives, but that they are defined in such a way that at least some of these objectives are conflicting with each other. So for example, I would like to design a bridge. I want the bridge to be as safe as possible, but at the same time, I would like the bridge to be as inexpensive as possible. Normally, if you want the bridge to be safer, you have to reinforce the structure, which means you have to spend more money, and vice versa. If you want to save some money, you have to make a lighter structure. So this is a good example of a multi-objective problem, which is defined this way. This is the traditional formal definition. We have K objectives, where K is greater or equal than 2, that we aim to optimize simultaneously. And we want to find a vector of decision variable that satisfy a number of constraints. We may have inequality and equality constraints. And basically, the main problem here, the main difficulty has to do with the conflict. Since we have conflicting objectives, this makes this problem ill-defined. It becomes really interesting. So the first issue in multi-objective optimization is how to define optimality. Optimality in the traditional way is kind of intuitive, is straightforward. But in multi-objective optimization, there are several definitions of optimality. The most commonly used refers to finding the best possible trade-offs. This notion was originally proposed by a professor at the University of Oxford, Francis Isidro Edgeworth, in his book entitled Mathematical Psychics in 1881. However, it was the Italian economist Vilfredo Pareto in 1896 who generalized this notion in a book called Cours d'économie politique, published in French, which at that time was the language of science. So, and he called it ophelinity. Is pretty much the same definition given by Edgeworth. However, Pareto was not aware of the work that had been done before by Edgeworth. The notion is very simple to define. If we assume that all the objectives need to be minimized, and this is always possible because if some of them have to be minimized and others have to be maximized, it's always possible to do a transformation. So if all of them are to be minimized, the definition of Pareto optimality says that a vector of decision variables that is feasible, that means it satisfies all the constraints of the problem, is considered Pareto optimal if these two conditions hold, that there is no other feasible solution such that is less equal in every objective and strictly less in at least one. There are variations of this definition. For example, if I remove the second condition, I only require the less equal. This is called weak optimality and generates more solutions than Pareto optimality. If I do the opposite, I remove the first and I only keep the second, the strict less, then this is called a strong optimality and generates less solutions than Pareto optimality. So this definition, basically what it says is that a solution is considered to be Pareto optimal if I cannot generate a solution that improves any of the objectives without worsening another one. So these solutions, since we get a set, constitute what we call the Pareto optimal set. We will get a set because of the conflicting objectives. And the vectors contained in this set are said to be non-dominated, but because of tradition, most people call them non-dominated solutions, which is mathematically is not correct, but everybody uses the term. And the image, that means the objective function values that correspond to the contents of the Pareto optimal set, is called the Pareto front. Of course, evolutionary algorithms or meta-heuristics were not the first option to solve multi-objective optimization problems, since these problems are very old. So multi-objective optimization as a research area started at around 1970 in operations research as a branch of mathematical programming. Of course, there are different types of multi-objective optimization problems. In this talk, I am referring mostly to nonlinear multi-objective optimization, but there is also linear multi-objective and there is also combinatorial multi-objective optimization. In mathematical programming for nonlinear multi-objective optimization, there are a number of techniques. I will say about 30 families. It's not really algorithms, it's families of algorithms. And these algorithms are very efficient, they're very fast. However, they have several limitations. The main ones are that they normally generate a single element of the Pareto optimal set for each execution. And if you execute the algorithm several times, starting from different starting points, there is no guarantee that at the end you will find a different solution. So this may require many different restarts of these algorithms. Also, these algorithms are very sensitive to the shape and the continuity of the Pareto front. For example, they don't work in many cases when the Pareto front is disconnected or is non-convex, when it's concave. The idea of using techniques based on the emulation of the mechanism of natural selections to solve problems is very old. Some people trace it back to the 1930s, some people like David Fogel. But it was really in the 1960s when the three main evolutionary algorithms were developed. Genetic algorithms were introduced by John Holland in 1962. Evolution strategies were introduced by Ingo Reichenberg and Hans-Paul Schwefel in 1965. And evolutionary programming was introduced by Lawrence Fogel between 1960 and 1966. Today, we call them collectively evolutionary algorithms. These are stochastic search techniques that try to simulate the process of natural evolution by imposing a selection of solutions based on fitness values. That's the main idea with these algorithms. Evolutionary algorithms seem particularly suitable for solving multi-objective optimization problems, mainly because of two reasons. The first is they can deal simultaneously with several solutions, with a set of solutions. This is called the population of the evolutionary algorithm. So this allows us, in case we can properly manipulate the population, to generate several members or elements of the Pareto optimal set in a single run, instead of having to perform several restarts as it is required with mathematical programming techniques. Additionally, evolutionary algorithms are less sensitive to the shape or continuity of the Pareto front. They don't require information such as the derivative of the objectives and the constraints. So they are more general in a sense. That doesn't mean they are always effective, of course. They also have limitations. The main limitation has to do with computational cost, because they require a sampling of the search space, and this sampling requires evaluating a certain number of solutions, which in some applications may be unaffordable, may be too costly to do. So considering multi-objective evolutionary algorithms, I'm going to show a very simple taxonomy starting from the old days. The old days is from the The origins of multi-objective evolutionary algorithms, they started in 1985 to the early 90s. This is the naive era of multi-objective optimization using evolutionary algorithms. So there were the non-norms. These are non-elitist, non-Pareto-based methods. That means they do not incorporate the notion of Pareto optimality in the selection mechanism, and they don't retain the non-dominated solutions generated at each generation, at each iteration. They don't keep these solutions, which theoretically is a problem because they cannot really guarantee performance. So these are normally very simple algorithms like lexicographic ordering, in which we optimize one objective at a time, or linear aggregating functions in which we add all the objectives into a single value. So we transform a vector optimization problem into a scalar optimization problem. Vega was actually the first multi-objective evolutionary algorithm, originally introduced in 1984 in the PhD thesis of David Schaefer and published in 1985. I'm not going to get into details on how it works, but it's a very, very simple approach that splits the population into subpopulations. And there are others like the epsilon constraint and the so-called target vector approaches, which can be seen as non-linear aggregating functions, but you need to define goals for each of the objectives. That means you need to have an idea of what values are you trying to obtain for each objective. Then from the early 90s to the mid 90s is when real research in this field started. These are the so-called non-elitist Pareto-based methods. These methods already incorporate the notion of Pareto optimality in their selection mechanism. However, they still don't use in a generalized way the notion of elitism, of retaining non-dominated solutions. So we have pure Pareto ranking. This is an idea that was introduced by David Goldberg in his famous book on genetic algorithms from 1989. It's basically a procedure for ranking or sorting the population based on Pareto optimality, such that solutions that are Pareto optimal get the best possible fitness, and all the other solutions will get an inferior fitness value, which is proportional to their level of dominance. The more solutions that dominate them, the lower their fitness value. That's really the idea of Pareto ranking, which has been adopted in different forms in the old days by algorithms like MOGA, proposed by Carlos Fonseca and Peter Fleming, NSGA, proposed by Kalya Moidev in 1994, MPGA, proposed by Jeffrey Horn. And there was also an MPGA2, but MPGA2 is a small and simple variation of MPGA. Then we have what I call the contemporary approaches. These are more elaborate algorithms. Some of these algorithms were the outcome of a PhD thesis. For example, the case of the strength Pareto evolutionary algorithm that was introduced by Eckhard Sitzler in 1998, although the journal version was published in 1999. There was a SPA2, but this version is also some sort of upgrade to the original version because the original one had some problems. Then, very famous, the NSGA2, introduced originally in the year 2000 in a conference, but the most cited reference is the journal version published in 2002. And there are, of course, many others, including some algorithms that we have developed in my research group, like the microgenetic algorithm for multi-objective optimization, and the second version, which is fully self-adaptive. That means no parameters are required. The recent approaches, these are approaches that belong to a third wave of algorithms in which there are other alternatives to perform selection, not only Pareto optimality. So these are very interesting algorithms, and many people are using them today. So we have, for example, MOIA-D, which is based on decomposition. Decomposition consists in transforming a multi-objective optimization problem into several single-objective optimization problems that are solved simultaneously. Then we have a family called indicator-based approaches, in which instead of using Pareto optimality, we use a performance indicator. to perform selection. There are algorithms such as SMS IMOA, HiPi, and many others, IBEA, the IBEA, many other algorithms based on this idea. And then we have NSGA3 and its many variants. NSGA3 is really based on reference vectors, so it can be seen like decomposition. It's not really a new family of algorithms. So in general, modern multi-objective evolutionary algorithms consist of two basic components: a selection mechanism that is not based on fitness, but it incorporates Pareto optimality. Some of these algorithms, they do use fitness values, but the fitness is computed based on Pareto optimality. The second component is not, you cannot find it in traditional evolutionary algorithms. This is a very interesting component. It's called the density estimator, and is responsible for maintaining diversity in the population, which keeps the algorithm from converging to a single solution. Today, we can identify three main families or types of multi-objective evolutionary algorithms that people are still using. So the first is the oldest one, the Pareto-based multi-objective evolutionary algorithms, in which selection is based on Pareto optimality. Most of them adopt something that is called non-dominated sorting. This is the ranking procedure to select solutions. And there is a wide variety of density estimators. I will show you on a slide later on. These are some of the names of the techniques that have been used. The main limitation of Pareto-based multi-objective evolutionary algorithms has to do with the scalability in objective function space. That means as you increase the number of objectives, these algorithms become less reliable. Why? Because in these cases, Pareto optimality is not good enough to identify solutions. Because as you increase the number of objectives, if you don't increase exponentially the population size, then first, the population is not large enough to sample the search space and generate a sufficient number of non-dominant solutions, but also most of the solutions will be non-dominated because the Pareto optimality relation is too orthogonal. It is possible, of course, to change the density estimator, and most of these algorithms still work, but not that many people like to do that. Second family, the composition-based, I already mentioned. In this case, you transform a multi-objective problem into several single-objective optimization problems, which are optimized simultaneously by using neighborhood search. That means some individuals are exploring not only their own single objective optimization, but also looking at the neighbors that surround them when doing the optimization. So these algorithms are very efficient. Unlike Pareto-based approaches, these algorithms are scalable. They can be used with more objectives. However, they still require a larger population size, although in this case, the increase in size is not exponential, it's normally linear, but it may be required to have a considerably large population size, not thousands, but perhaps hundreds of solutions, depending on how many objectives you have. And they have other limitations. It was found relatively recently that one of the limitations they have is the shape of the Pareto form, that they don't work with certain shapes. Finally, we have indicator-based. This is a very interesting family. In this case, the idea, as I said before, is to use a performance indicator to select solutions instead of using Pareto optimality or instead of using decomposition. However, some indicator-based algorithms use decomposition as well. The problem here is, this is a very intriguing, very interesting idea, but the problem is we only know one performance indicator which is fully Pareto compliant, and it is very expensive. It's called the hyperbola. There are other performance indicators that are what we call weakly Pareto compliant, but for some reason, researchers don't seem to like them too much. In practice, they are not that bad. Most of them work reasonably well, but they are not very popular. For density estimators, as I mentioned before, there have been many different proposals. These are the most commonly adopted today, going from fitness sharing, which is one of the oldest. This is scalable, same as clustering. Other approaches are not scalable. For example, the adaptive grids, which is some sort of geographical map in which you locate solutions. Crowding also is not scalable. Performance indicators are scalable. Parallel coordinates, this is one we proposed some years ago in 2016. This one is scalable. And this, I always like to show this graph that shows the number of publications per year in the field. This tells you about the growth of the field. So you can see that it started in 1984 with the PhD thesis of David Schaefer. I got my PhD in 96. And at that time, very few people were doing IMO. We actually knew each other, like, for example, Carlos Fonseca, Jeffrey Horn, very few people. However, in a very short time, like, for example, by the year 2009, 2010, you can see a very, very large number of publications per year. Actually, we have reached more than 1,000 publications a year. When I got my PhD, my thesis was probably number 5 in the field. But today there are more than 300, probably more than 400 PhD theses on IMO that we know of. There may be more. In recent years, some people sometimes ask me if there has been a decrease in the number of publications on IMO because the bars are getting smaller, but there is no decrease. It's a decrease in my time, the time available for me to update this graph, but there is still a lot of interest. So very quickly, I will go through a few applications, not specific to big data. These are applications in general that can give you a broader idea of the many uses of IMO. IMO has been used for also for big data and for other applications related to modeling diseases and so on. But these are more general. So the first is a proposal to assist architects in the design of a particular space. So the idea here is to learn heuristic rules on building a spatial design by using data mining on results generated by a multi-objective evolutionary algorithm. It's a very interesting proposal in which the human benefits from the solutions generated by an evolutionary algorithm to try to learn a little bit about the best design practices for optimizing certain objectives. In this case, for example, the structural or thermal performance of the specific architectural space. This was done in the Netherlands. The second one, it's also very interesting application in medicine. These guys in UK, they use a multi-objective meta-heuristic to optimize the intensity modulated radiation therapy for cancer treatment. So in this case, the idea is to find a set of dose distributions that, depending on the prescription and the preferences given by the physician, can be selected as the preferred treatment for a patient. So these treatments have to be very specific. And in this case, they are using multi-objective optimization to help the physician to find the best possible treatment. The next one is one in software engineering. This is for a company that develops software. And in this case, MoIAD, an algorithm that I already described, is extended to solve software project portfolio optimization problems. In this case, the company has a set of projects. They don't know on which ones it is worth investing money because they have a limited budget. And the idea is to use the multi-objective evolutionary algorithm to decide which are the projects in which it's worth investing to maximize return with limited resources. And of course, these are problems in which there are many, many constraints, like related to marketing, to distribution channels, and so on. This was done in China. And the last one, this one is from India, is an application of another meta-heuristic. It's not an evolutionary algorithm, the multi-objective and colony optimization for solving gas transportation problems. In this case, the idea is to minimize fuel consumption and maximizing throughput. That means the efficiency in transporting gas. So in this case, they propose this approach for optimizing the operation of pipeline network. And it's also, this is a real world application. It's also another very interesting application. In all these cases, you can see the objectives are really conflicting because improving one normally worsens the other one. So in terms of research, what we do in this area, besides developing algorithms, which is what we do in my research group, is we're interested, for example, in hybrids between multi-objective evolutionary algorithms and mathematical programming techniques, for example, gradient-based methods, but it could be also direct search methods. We have a lot of interest on surrogate and parallel implementation techniques to deal with very expensive objective functions, for example, those found in some applications in bioinformatics, in aeronautical engineering, and so on. There are, of course, people developing many applications in different fields, and there are many other research topics. I won't get into them because they are a bit more specific, more specialized. Some of the challenges involve, for example, solving problems having a very large number of decision variables. For example, what if we have 10,000 decision variables? Can we solve a problem like that? Also, for example, combining different operators and algorithmic components, selection, crossover, mutation, and so on, to produce tailored multi-objective evolutionary algorithms that are highly competitive for a particular application. Of course, for us to be able to produce something like this, it's necessary to do a lot of, to perform lots of experiments combining these components. So this may require a lot of computational resources, but there are already approaches like this. There is one called BORC, developed by a guy at Cornell. And there are many other questions, for example, related to density estimators in high dimensional objective search space, objective function spaces. What happens regardless diversity, we have 10 objectives. So if you are interested in this topic, you are welcome to visit the EMOR repository, which very quickly I will show you. It contains more than 12,000 bibliographic references, including more than 300 PhD theses and more than 6,000 journal papers. You can also find public domain software in different programming languages, in C, C++, Java, Python, MATLAB, and so on. And even some platform, like there is one called PlatEmo, that contains more than 100 multi-objective evolutionary algorithms already implemented, and you can get it for free. So that's all from my side, and if we still have time, I'm open for any questions. Thanks a lot.